Alright, this is our lesson for January 22nd, and what we need to cover is a lot of stuff actually, so we're going to jump right into it. You guys don't even have a bell ringer today because I think we're getting a little bit behind from where I want us to be, so we're just going to push on through this stuff, and then after we do this, we're going to cover oxidation states. Then we're going to look at types of reactions. And then after we've gone through all the types of reactions, we're going to jump back and go to the activity series of metals, which is a little bit different than what he does in the chapter, but I wanted it this way. And then you guys are going to review homework and work through a couple of those on balancing equations. And then maybe do some examples of these if you have time. Let's say examples of today's material. Okay. And what we're going to do is we're going to get a little bit, spend a little bit more time. Why are you not focused? Get focused, camera. And the quiz, we're gonna push it back. We just need some more time to get into this material. And so the quiz was supposed to be, what did I say it was going to be? Quiz was going to be the 24th, and I'm gonna push it back to the 29th. Okay, and that means the test is going to be pushed back, I think, because we got just a lot of stuff to cover there with limiting reactant and theoretical yield and other stoichiometry stuff there, so that'll mean that'll be February 5th. Okay. All right, let's dive into it. Okay. All right, so we're just going to pick up right where we left off in the book anyway, and we're going to talk about oxidation states. Okay, now I think I have been using that terminology since we started talking about, like, for example, sodium tends to take a +1 charge when it binds in ionic compounds. Okay, and when those come together, you know, with an NaCl with a total charge of 0, right? Okay, so what he wants to do, we actually, chapter 12 is actually redox equations, okay, redox chemistry, and I'm just not super familiar with all of that, and I have not had time to really review the entire chapter 12 and where that goes. So, but I know that chapter 12 references this. So I think this is just to introduce the concept to you while we're starting to talk about all the different types of reactions, and then we're going to come back and sort of review that in much more depth. Okay, so right now let's just start out with, we have two mnemonics, right? And the one I learned was oil rig, and I think is actually a better mnemonic. All right, and so what has he got? He's got, he shows us right here. Okay, Leo the lion says grr. All right, so Leo lose electrons and oxidize. There we go. And grr, gain electrons, reduce. Okay. And so the same thing, oxidation is loss, reduction is gain. Okay. Reduction is gaining. Okay. So what does that mean? Okay. So here's the key concept that we need to make sure that we are aware of, is that unbonded atom oxidation state 0. Okay? So if we're gaining and losing, we ought to be gaining and losing from something. Okay? And so we start out at 0. All right, so to go back here, all right, so really in this ends up as a +1 and a -1 while we're in here. And so what happens with sodium? All right, if everything is unbonded while they're just floating around, and we'll call this, okay. Now, of course, this was actually floating around as Cl2. Okay. All right, we're just kind of zooming in on a very specific thing here that's got to do with the specific electron configuration. Okay, so we're not worried about this so much as we are just knowing that anything in an unbonded or bonded to itself, okay, that's a good point, unbonded or self-bonded, right, like Cl2, O2, any of those guys. Everybody else, we're just going to assume they're in their pure state when we're talking about redox stuff here. Okay. All right. So what does it do? It goes from, so sodium goes from 0 to 1+. So what is that? That is a positive, so it has lost electrons, right? And that's what we talked about with the ionic bonding, right? That sodium actually gives up an electron to the chlorine to complete the chlorine's octet, and for him to lose that extra pesky electron. Okay, and so then chlorine goes from 0 to 1-. So it's pitiful G, isn't it? Golly, that poor guy. He must have gotten picked on when he was a kid. He was so small. There we go. Make him a little bigger. All right. So he gained electrons. All right. So chlorine is oxidized. No, wait. Hold on. Let's see. Sodium loses electrons, and so he's oxidized. Chlorine is the, yeah, right. Okay. Sorry, I was looking at this paragraph below that and said if the chemistry is driven in the opposite direction, it tells you what happened. And I was like, wow, that's totally not what I was just saying. All right, so gain, so he is reduced, and he is oxidized. OLOLRGRG. Okay? Alright? So it is oxidized and it is reduced. Okay? So if it is reduced, it actually is the oxidizer. Man, I'm in some trouble, guys. Oxidizer. Okay? Alright. So, in the converse is true here as well. Lost electron is oxidized, so he is the reducer. Okay? Sodium reduces chlorine. So chlorine is reduced and sodium is the reducer. Sodium is oxidized, which means chlorine is the oxidizer. Okay? So it's a mutual deal here. Alright, so I guess I'm trying not to confuse you guys with just too much stuff. So we say like this, reduces chlorine, which oxidizes that. Okay, so that's sort of what's going on there in that circular electron pattern right there. Okay? And then from there, we're going to roll with that. And then let's look through these rules. All right. Oxidation states the elements must add up to the charge on the molecule. Okay, so we just talked about that. And that kind of makes sense why something that is self-bonded, like a Cl2, the total is 0. Well, one can't be a plus chlorine and one can't be a minus chlorine because they're identical. So they both must be a 0 plus 0 equals 0. So the oxidation state in that stage is 0. Okay? In a polyatomic ion, they must add to the charge on the ion. Okay, so we talked a little bit about that back in, I don't know, November, October, or something like that. We were talking about polyatomic ions. All right? Pure elements, oxidation is 0. Applies to diatomic ones and ones that like S8 and P4. Anything is bonded to itself. All right? So then we have, in order of sort of supremacy here, we go in the most electronegative, and that kind of sets the stage. So fluorine, you guys remember, is the most electronegative, okay, and it's a -1. So anytime you see fluorine in a compound, you know that that is going to be a -1, okay? And then oxygen is right after that, and it's a -2, okay? Obviously, one exception here, if we see an H2O2, hydrogen can't be a +2, so it's got oxidation ends up being just -1, and we know that because I think we're just going to have to get a lot into that, okay, later, because we don't have a whole lot of time to go into it right now. But we see here that your O2 as a peroxide, it only has a 2- charge. Okay, I will try to find an answer for how they know that, because I do not know at this time. I don't know why they don't just assume that that's a 4-, So we're just gonna roll with that. No, peroxide is an exception there. All right. Then once we get past those, oxidation number for halogens is -1, unless they bond with oxygen, unless it's a fluorine. Okay. So we'll run through some of these. Hydrogen forms a compound with an element that is more electronegative than itself. Its oxidation state is +1. In compounds with metals, the oxidation state of H is a -1. And to be honest, I can't remember exactly how much we talked about this, before. So if we just look at, H2O is our favorite example for pretty much everything, which is good because it's common and fairly simple, and it works for like a lot of different things. All right, so what is this? We start out and we don't have a fluorine, so our next one is that we set this as a 2-. Okay, and so that means that this together has got to be a 2+, and there are 2 of them, so H, each one of them is just a plus. Okay, so we're able to say that if we let's say we were to do this same analysis right here on water, what would end up being the case? Okay, so we had some H2 floating around. Okay, and he meets up with some O2. Okay, and they end up as water. Okay, so let's write that as an equation. We have H2 plus O2 goes to H2O. Okay, we won't worry about the states or any of that stuff right now. Okay, let's balance it. We got 1 right here, 2 over here. So let's go ahead and put a 2 right there. Okay, now the oxygens are balanced. 2 oxygens, 4 hydrogens. Let's put 1 right there. Okay, so now we have a balanced equation. What's the oxidation state of this? Well, it's bonded to itself, so it's a 0. Also bonded to itself, so it's a 0. Okay, now let's look right here. We know that this is a 2- in this situation, and this must be a 1+ in this situation. So what is this? We have hydrogen goes from 0 to a 1+, which is what? That's losing electrons, which means it's oxidized. Okay? Which makes sense because often oxygen is the one doing the oxidizing. Okay? Which means that oxygen is often reduced. Okay? And so he's gaining electrons and is reduced. And because he's reduced, he is the oxidizing agent. Same thing here. So we could write H reduces oxygen, which understandably why it's called that. That. Okay. We could also write is oxidized by and is reduced by. Either one of those completes this thing correctly. All right, that's enough of that. We'll come back to that. We'll learn it. We'll be super into it. Okay, really fast. Let's talk about these. MgCl2. This is a halogen, so we know that it's a -1 because there's none of the other rules above it that overtake that. And if that's a -1, we've got 2 of them. The magnesium has got to be a +2 to make the whole thing be 0. Okay. F6. Each one of those is a -1, so that's a -6. That means this sulfur's got to be a +6. okay, which is a very large number for an oxidation number. Okay, normally they're like +1, +2, +3, but very rarely do they get up as high as 6. Although often within complex covalent molecules they do that. Okay, that is pretty high still, even for a covalent molecule. All right, look at this, BaO2. Let's see, the oxidation state of the metal is the one that I want to show. Okay, this is interesting. I don't know how we would know this, just out of the blue. I guess from the name we would know that in this peroxide situation, that oxygen has a -1, which is just a +2. We need to look more into this, and rest assured, I'm not going to ask you specific questions about that until I understand and explain to y'all in a way that I feel like y'all can understand. So just note that sometimes oxygen acts a little funny, but typically when we're looking at it, it's going to have a -2. All right, so this one gets a little bit more complicated. HClO3, okay? Chlorate, okay? It's an oxyanion, so it says, again, I'm not super sure how we are supposed to know these things here. So we'll make a note here. Let me do some more reading about this, and I'll get back to you guys on that. All right, we're going to stick with pretty straightforward stuff until I've got a better handle on that and can do a better job explaining it. All right, excellent. All right, on to the more meaty stuff here. All right, so this is interesting stuff here, and it's important. So really get your attention, I guess, focused on this. All right, so we got a bunch of different types of reactions, and the reason we are going to talk about these is because they help us to know what to do with the equations when we're writing the chemical reaction equations, okay, and going to balance them. We can kind of know a little bit more what to expect when stuff fits in one of these patterns. All right, so they're pretty straightforward as far as their names. All right, so let's just jump right in. All right, so if we synthesize something, that means we make it. Okay. So we're going to take the pieces and parts of something, and we're going to make them into something more. So we're going to take an A part and a B part, and we're going to make them into an AB. Okay? And we don't know anything about A and B other than they were separate and now they're together. So let's say hydrogen and oxygen coming together to make H2O. Okay? Pretty straightforward. Doesn't matter whether there's a 2 or a 1 or a 12 down here. All we know is that there were two separate elements and now they're together in a compound. Okay? The flip of that is decomposition. Okay? When a body decomposes, perhaps after you bury them, all right, it was together and now it breaks apart. Okay? And he gives the example. We have H2CO3 becomes H2O and CO2. We're not fooling around with any balancing or any of that stuff right now. Okay? Something is breaking apart. We'll come back to all of these right now. All right, we're going to skip over the activity series of metal if y'all are following along. All right, so just flip on through. We'll come back to that. Okay, so we have double replacement. Let's take a compound AB and another compound CD. All right. And what's going to happen is that A and C are going to swap places. Or you can think of it as B and D swapping places. It doesn't matter. They're the same thing. But what we end up with is AD and BC. Okay? And a lot of times these, I said elements earlier, but they can also be polyatomic ions. Any unit that hangs around. Okay? So he's got copper nitrate. And H2S, CuS, and HNO3. Okay, so what's happened? This S has left the H and gone to the copper, and the sodium has gone to hydrogen. Okay, so this guy has come in and pushed him out, and he's gone free and then joined up with him. Okay? Pretty straightforward to see why they're called that. Okay? So that's, we now have a single replacement? Oh, he talked about that in the activity series. Okay? So this is double replacement. Alright, and then we have a slightly simpler single replacement. Okay, and that's where you have an AB plus a C goes to an AC plus a B. Okay, and we'll see how that sometimes happens with the activity series of metals in just a second. Okay. So what happens is the C comes in and kicks that B out and takes his place. Okay? One we're so inclined, one can think of this as relationships. Okay? These two are dating, and these two are dating, and now they're dating each other's exes here. Okay? These two are dating, and the new guy comes to town and kicks the one on. Now he's single. Okay? However it helps to think about it. All right, and then we have combustion. All right, and so we've talked about we know about the internal combustion engine. All right, so combustion is basically burning, which is a special form of oxidation. Okay, and so you always have a hydrocarbon plus oxygen, and it goes to water and CO2. Okay, and I put an X and an X here because they all can do it. Okay, they follow the same thing. Now, in real life, this doesn't happen in a perfect way, and so you end up with all sorts of things like, you've heard about cars produce carbon monoxide, okay, CO. Okay, and that's because the temperatures are not right, or there's not enough oxygen in every single place, or various numbers of reasons. But in an ideal basic situation, we have the hydrocarbon in an atmosphere of oxygen, and it only produces H2O and CO2. Okay, and just so you know, This is the central driver behind the rise of CO2 levels in the atmosphere over the last 100 years. Okay, so that's what people are, so they're talking about. It's primarily from the burning of fossil fuels, which are could be methane, which he talks about right here in the chapter. We've also got those long chain oils that would come out of crude oil that form up gasoline and octanes and heptanes and all that stuff. We're burning those, and this is the primary reaction. Even though there's all this other stuff, those long chain carbons that are found in fossil fuels release a lot of energy when you break them up into these single carbon CO2 molecules. Okay, so just keep that in mind as we talk about things like that. This is the driver behind all of that discussion about CO2. All right, then we have acid base neutralization. Okay, and it's just easiest to probably look at explaining this. So we've got HCl, MgOH2, MgCl2 plus 2H2O. Okay. All right. So what do we start out with? This is hydrochloric acid, and this is magnesium hydroxide, a very strong base. Okay, mix them together. They have a neutralization reaction, and what do we end up with? A salt and water. Okay, so at its core, we have an acid plus a base goes to a salt and water. Okay, and he talks about how salt is actually defined as the result of a neutralization reaction. Okay, and so we could do, this could have been also HCl plus sodium hydroxide. And what would that form? Well, this and this would get together and form H2O and NaCl. Okay, which is pretty amazing that you could take hydrochloric acid and sodium hydroxide, both of which would, in proper strength, burn the skin off of you, and you mix them together, and literally all you get is salt water. That you could take a Morton salt thing, pour it into water, mix it up, and that would be the same byproduct or same set of products as these two strong acids and bases that are utterly poisonous to you would just become this. It's kind of crazy. All right. So let's now go back to the activity series. Okay. And figure out what that means. All right. So you need to be able to identify from the chemical reaction equation here whether something is synthesis, decomposition, single replacement, double replacement, combustion, or an acid-base neutralization reaction. Okay? They all look very distinct, so if you just think carefully about it, you should be able to identify them without any problem. Okay? All right. So the metal activity series. All right, you can follow along. Now this is page 181. All right, and so all we're doing is we are looking at metals and figuring out which ones will react and which ones won't. Okay, in certain situations. All right, and this is key right here. Chemical activity of the metals was determined empirically. All right, what does that mean? It means they didn't know either when they were doing this, and they just did experiment after experiment and then got them all in order. Okay, so active metals like lithium react very strong in water. Okay, and so basically we have these very reactive ones up here and going less and less reactive until we get down to the bottom here where they're not very reactive at all. Okay. All right. I had to get some water there. Sorry. All right. So let's look at how we actually start to use some of this when we're looking at equations. I think it's most helpful to go straight to what the actual equations look like. All right. So we've got a iron nail is what he has right here. So steel nail is placed in the container of copper 2 chloride. So let's just look at that. All right, so we got the copper chloride right here. Okay, and we put an iron. It says steel, but it's mostly iron. So put that in here, and then we look over here at our activity table. Here's iron right here, and here's copper down here. More active, less active. Okay, so the more active copper comes in and sort of butts his way into this solution, into this compound, and now that copper is free floating, and these are now in solution to get as a compound together. Okay, now we remember that a solution is where you've got these ions kind of floating free in the liquid, but if we were to get rid of the liquid, like evaporate the water, this is what the solid that would result. So we'd have copper solid and we'd have iron chloride solid here. Okay, and he points that out here. As we explore further in chapter 10, this means that copper and chlorine ions have dissociated in the water. The crystal comes apart and the individual ions are separated from each other. Iron is a more active metal than copper, so when the steel nail is placed, the Fe ions are oxidized, and we could look at those oxidation states to make sure that we understood what was going on there. Okay. To become Fe2 plus ions in solution, right? And so this is an interesting thing. This is not just a representation. These are actual electrons coming off of the actual iron things and being free floating in the solution. And so when we talk about electrochemistry a little bit later, that's exactly what is happening, is then those electrons become free floating, and we can actually harness that as a current and generate electricity, which is how batteries, how chemical batteries operate. Okay? You actually have one metal decaying and pushing its electrons through a wire to the other side.
Okay, and we'll talk more about that. All right. The copper ions are reduced to become Cu atoms, which is why they are now, because we know that any lone atom has a 0. Okay, so they go from 2 plus to 0, meaning they've gained electrons, which is being reduced. Right, and so they precipitate onto the steel nail. That doesn't really matter for as far as this. That's physically where they end up. All right, and so the second type, which is a metal replacing. Oh, sorry, I underlined these and didn't tell you a lot. All right, one metal replacing another in solution, which is what we're talking about. A metal replacing some of the hydrogen atoms in water. Okay, so let's talk about that. So we've got sodium metal. Now this is not, don't confuse that with salt, sodium chloride. Sodium metal. Put it in water, and it's very, very reactive. Okay, sodium is way up here, very reactive. All right, and what it does is it boots one of these hydrogens out and replaces it with a sodium. Okay, and that frees this hydrogen up as gas. All right, and then finally, metal replacing the hydrogen atoms in acid to form a salt. Okay, so we got right here. This magnesium comes in and poof, pushes that hydrogen out. Now he's bonded with this, and the hydrogen is liberated as gas. Okay, and that's that. All right. So the way to be able to tell when we're looking at something now, if I put something in there, and these are our more reactive and our less reactive. Okay. So if you come in and you put a copper, let's say you put a copper nail in a zinc chloride solution, okay, it's not going to do anything because the copper is less reactive, so he's not going to have the, sort of quote unquote chemical strength to push that zinc out of the way. Okay. Similarly, if we put a zinc nail in aluminum chloride, not going to do anything. Okay. But this is why you have to be very careful when you're building things with treated lumber, because that's treated with a copper solution with some copper hexachromate or something like that. All right. So, but there are these copper things that are in a compound in that treated wood. You use treated wood when you're building a deck or doing something outside, and it doesn't rot nearly as quickly as regular wood does or untreated wood does. But if you come in and you use zinc-plated nails or zinc-plated screws, okay, often exterior stuff is zinc-plated to help it last longer. Well, what it does is it comes in, and zinc is much more reactive than the copper, and so it comes in there and it starts to replace those copper ions, and it totally changes what goes on in there. The nails lose their zinc covering because the zinc is going to react with this, and eventually loses its covering and it rusts away, and then your deck falls apart because everything's rusted. So you have to use the proper fasteners so that the zinc doesn't come in and react and boot that copper out of place. Okay? All right, so you guys are going to go on and you're going to do some of this for homework, okay? But you guys are going to review your balancing equations homework, Ms. Barron, and then if you guys have some time, work some examples of today's materials based on some of the back of the chapter there. I don't know how much time you're actually going to have, though. So, yes, really, the back of the chapter ones right here are going to be very helpful as you go through those, because we do have this quiz coming up on the 29th. Like I said, we're going to push that back. I'm going to fix the assignment sheet so you know what's going on, and then we'll have that test on 2/5/19, and quizzes are going to be graded soon. They are actually still in a certain box at the school and are coming home today, hopefully. And so I'll get those graded as quickly as I can for y'all and get those grades put up there. I'm also going to go through, if not today, then tomorrow, and make sure you guys' grades are all up to date, and I'll put in grades that anything I'm missing so you guys can look and see where we are on that before we get too much further in the year. All right, so a lot of nuts and bolts here. Not a lot of super exciting, flashy videos or anything like that, but some good information. Do store this oil rig, Leo GUR, Leo Alliance's GUR, whichever one works better for you. Go ahead and store that away. Okay, be thinking about what it means to lose and gain electrons and which one is which. Read that a number of times because it's going to come back again in chapter 12. It's basically going to be the same information but a little bit more in depth. Okay, so it's not going away. You're not just going to make it through quiz and through test and then be done with it. It's going to come back again. I will probably end up handing out an activity series of the metals for you guys to use. There will not be any memorization involved in this because that's totally pointless. You will have to use those at certain points to answer questions about whether a reaction will happen or not, and what kind of reactions that will be if it does happen. All right, next time we will pick up with stoichiometry and a lot of fun stuff there, which will actually just start getting us prepared for one of our experiments. And talk about limiting reactants next time, and we'll just keep plugging and working problems and all that. All right, we'll talk to you guys soon. Thanks. Bye.